In the previous lecture, we started the discussion on binary arithmetic, and in particular, we discussed things like conversion from the decimal to the binary, binary to the decimal number system. We also discussed about the hexadecimal number system and the very direct relationship it has with the binary number system. Thereafter, we discussed something called binary addition. So therefore, let's quickly recap that. So we had said that when you're adding two binary bits or two binary digits, in general, you can have a 2-bit answer. One bit is the sum, which is always there. The other bit is the carry, which is very similar to the carryover, which we have learnt in our basic addition since the school days. So therefore, whenever you're adding two numbers, you have things called two outputs, the carry and the sum. So if I'm adding 0 plus 0, then the sum is 0, even the carry is 0. When I'm adding 0 plus 1, in that case, the sum becomes 1, but the carry remains 0. When I'm adding 1 plus 0, in that case, the sum is 1, the carry is 0. Addition is a commutative operation. So therefore, no matter which way you add two bits, the result will remain the same. And here, if we have 1 plus 1, in that case, the sum is 0, but the carry is 1. So this is addition. Please note, this is not OR operation. Now, something to note very interestingly is if you were to picture this entire thing as a truth table, let us say if this bit I call as A, this I call as B, then if you notice something very interesting, the carry column resembles an AND operation of A and B, and the sum column represents an XOR operation. So therefore, you can now see that indeed the sum, which is an XOR operation of the two bits A and B, shows that even though the XOR gate, the XOR logic gate we discussed few classes back, is neither a universal gate nor a basic gate, it still has important mathematical repercussions as far as binary arithmetic is concerned. So therefore, I can say that carry is equal to A dot B and sum is equal to A XOR B. So therefore, if you want to make a very simple circuit that can add two binary bits, all you need is an AND gate and an XOR gate. Right? So this is where we are trying to establish a relation between the mathematical operations in binary versus the logic gates that we have learned about. Okay. So having established the basic principles of binary addition, in the previous lecture, we also looked at a couple of examples of binary addition, and we verified that they were indeed correct by converting each of those two numbers and the sum into the decimal form and cross-checking with that. That is a very quick sanity check that you can do. Now, let us look at what is binary subtraction. So where we have, let us say, two bits, what we will do is A minus B. Okay. So definitely when I'm doing A minus B, now we will not have anything called a sum, we will have something called as a difference. So therefore, if I am doing 0 minus 0, then if I am writing the difference is 0. If I am doing, let us say, 1 minus 0, the difference will be 1. If I am doing 1 minus 1, then the difference is 0. Now, the fourth case is very, very interesting. When I am doing 0 minus 1, in that case, what would be the difference? In this case, what would be the difference? Now, what you are noticing is that the first number is small and the next number is larger. So therefore, the concept of negative numbers come into picture. But I'm sure when we all learned about subtraction as a mathematical or arithmetic operation during our school days, we learned it at a very early age, and probably at that time we didn't even know that negative numbers existed. Then in that case, how did we learn subtracting one bigger number from a smaller number? We used the concept of something called as a borrow. So therefore, this is, in this case, 0 minus 1, the difference is still 1. However, we call it 1 with a borrow of 1. What was carry in the case of sum becomes borrow in the case of difference. Let us take a look at it with an example. Let us first take a very simple example. Let us take a very simple example. Let's say I have two binary numbers. I am doing this. So if I am subtracting 0 minus 0 is 0, 1 minus 1 is 0, 1 minus 0 is 1, and 1 minus 1 is 0. This was a very simple operation where there was no involvement of any borrows. Okay, so we can very quickly check what these numbers are. So in decimal, this is 8 plus 4 plus 2, that is 14 in decimal. And this one is 8 plus 2, that is 10. So the difference is 4, which is the same as we had obtained in the binary operation. Now let us try a very simple example with a borrow. Let us say I have 1, 1, 1, 0 minus 0, 1, 0, 1. Now we have a 0 of minus 1 in the rightmost side. So 0 minus 1, the difference is 1. But I am doing this by taking a borrow of 1. Means from the next higher position of the first number, I am borrowing the 1. So if this 1 is borrowed and it's brought over here, so therefore effectively this would become now a 0. This would now become a 0. So therefore, now that I have borrowed the 1 and brought it over here, and what I have left in this 2th place is the 0 over here. So 0 minus 0 is still 0. 1 minus 1 is 0 and 1 minus 0 is 1. So once again, let us verify. This is 14 in decimal. This is 4 plus 1, 5. So therefore, the answer must be 9. In this case, what I am saying, it is 8 plus 1, 9, which is correct. Now, what may happen is, this was a pretty simple example of borrow. You can try out some other examples all by yourself, just to make sure you understand the principle of borrow. Now, what may happen is that while it is fairly easy to work with carry, I as a student, when I was a very young child and learning the borrow subtraction for the first time, I was not very comfortable with it. Of course, it does not mean that people will not be comfortable. But then, what we had done was that to look for ways in which we could do the subtraction without using the borrow. So therefore, to understand borrow, let us look at some decimal number examples. Let us say I am learning decimal subtraction. Let us say I have 96 minus 57. So obviously 6 is less than 7. So what I will do, I will borrow 1 from 9. So what will happen is this will become 1 6 or 16 and this will become 8. So 16 minus 7 is 9 and 8 minus 5 is 3. This is the answer. So although this looks very simple now, when we have more number of digits in the given problem, borrowing for multiple stages could be a bit of a bother. So therefore, the question now is that is there any way to do subtraction without using borrow? Without using borrow. Therefore, let's investigate that. Subtraction without using borrow. Let's look at the decimal numbers first. Let's say, for the sake of simplicity, I will take two numbers and try to subtract one from the other, and I'll take two assumptions. One is that I will subtract the smaller number from the bigger number so that the result will be positive. And the number of digits in each number would be the same. So therefore, without the loss of generality, let us take the example of two-digit numbers. Let's say I will say 86 minus 58. I want to do this operation. First, let us do this conventional using borrow. The result would be, if I borrow a 1 from here, 16 minus 8, it will be 8, and here it will be 2. So the answer is 28. So using borrow method, I am getting 28. Now let me do this in a different way. The question is 86 minus 58 in decimal. I will look at the second number, that is 58, and subtract it from the largest two-digit number. So which is the largest two-digit number? The largest two-digit number is 99. So therefore what I will do, I will subtract 58 from 99. In this case, there will never ever be a borrow because this is the largest possible two-digit number. So therefore the answer is 41. Yes, it is 41. Now when I have 41, I will go back to my first number. And what I will do is I will use the first number 86 and add this 41 to it. So what I will get is 7, 1, 2. So answer is 127. Now what I am noticing is that the numbers are each of 2 digits, but the result is of 3 digits. So therefore what I will do is that I will take this one and add it over here. So therefore I will have 27 plus this one. The answer is 28, which is exactly the same as which we obtain using the borrow method. Now take a couple of moments for this to sink in. What am I doing? I am doing the operation of subtraction wherein the second number or the smaller number, I am subtracting it from the largest possible n-digit number. So if these numbers were of 3 digits, then you will subtract from 999. It's like that. And then the result is being added to the first number. And the extra one that comes, this is what is called as the carry. This extra carry is added and you get the final answer. So therefore this process where we are actually subtracting from the largest two-digit number, this technique is called as the 9's complement technique. Ninth complement technique. Similarly, let us look at another technique which is a very slight modification of this, where rather than adding the 1 at the end, we are going to pre-add the 1. Let's take the same number or the same set of numbers, that is 86 minus 58. Once again, I will subtract the second number from 99. I will get 41. What I will do, I will add 1 here itself, that is 42. Finally, when I subtract this from the first number, 86 minus 42, sorry, it's plus 42, it will be, in this case what you can do, you can simply discard this one and the answer is 28. This technique, where we are following largely the same steps as that of the 9's complement method, but we are adding the 1 beforehand rather than at the end. This technique is called as the 10's complement technique. So, why we are discussing the 9's and 10's complement is not because I, as the instructor of this course, found it difficult in childhood to handle borrows in subtraction. No, that's not the way. Rather, I am discussing these techniques because even in computers, it is easier for processors to understand carry as opposed to a borrow. Borrow is something which is very, very difficult to be, at times, to be implemented in logic. Not that it cannot be implemented, but often scientists have looked at easier ways. So in decimal number system, we have two techniques to use without borrow. One is called the 9's complement, the other is called as a 10's complement. So which I am shortening and writing it as 9C and 10C. Therefore, in binary system, these equivalent techniques are called as the 1's complement and the 2's complement. Alright? So therefore, let us take an example and see it. Let's take the same set of numbers which we took in the previous example when we were learning with borrow. So let us say I have 1110 minus 0101. I am just trying to ensure that the number of digits for both numbers, both input numbers are the same. So therefore what I will do, I will take the second number and subtract it from the largest possible 4-bit binary number. So I will say the 1's complement of 0101 is what? It is 1111 minus 0101, which is 1010. You will notice very interestingly that you don't need to do this operation. If you are calculating the 1's complement of any n-bit number, all you need to do is replace the 1's with zeros and the zeros with 1's. Alright? So then the second step is add this to the first number. Okay. So what we will do is this addition. 0 plus 0 is 0. 1 plus 1 is 0 with a carry of 1. 1 plus 1 is 0 with a carry of 1. 1 plus 1 is 0 with a carry of 1 over here, and that 0 plus 1 is 1, like this. So therefore, in 1's complement, we will do this operation where we add the 1 over here, and the answer is 1001, which is the same as what we had got in the technique or the approach using the borrow method. So this particular step where we have to take this 1 and add it back over here This is called as end around carry. End around carry. Now let us do the same operation but using 2's complement. So in 2's complement, we first calculate the 1's complement and then add a 1 to it. So 1c of 0101 is nothing but 1010. Just replace the zeros with 1's and 1's with zeros. So 2c of this number would be this plus 1, which is 1011. So again, add it to the first number, 1110 plus 1011. This is 0 with a carry of 1, 0 with a carry of 1, 1 with a carry of 1. So in case of 2's complement, we will just ignore this, and this is the answer. So 2's complement is always a little better for the computer to use, because it is always easier for the computer to ignore the 1 rather than bringing it back and adding it. Okay, so this is what is meant by 1's complement and 2's complement. So therefore, we can now redefine that binary subtraction is nothing but 1's complement addition or 2's complement addition. So what we are essentially doing is that the subtraction method we are converting into addition. Alright? Now, notice that there is an extra carry bit in case of both 1 complement and 2's complement. Of course, in the case of 1's complement, this extra carry is utilized as an end around carry, and in case of 2's complement, this carry is just ignored. But nonetheless, in both cases, irrespective of whether it is added or whether it is ignored, they convey a very distinct message. They convey a very distinct message. What is that message? Let's see what it is. Let us now try to do an operation which is 10 minus 15. Let's convert them into binary. In 4-bit binary, this is 1010, and here it is 1111. Notice what is happening. We are now trying to be brave and trying to do a subtraction where the second number is bigger than the first number. So in such a case, what you will see is that if I try to do this, let us say 1010 minus 1111. Okay, if I try to do this, let us try to do this with a 2's complement technique. So therefore, 2's complement 1111. How do you calculate it? The 1's complement of 1111 is 0000. And then I have to add a 1, which is 0001. Now what I will do, I will add it to the first number. So 1010 plus 0001. The answer is 1101. Now notice something very interesting. That additional bit to be ignored is not there. That additional bit to be ignored is not there. So therefore, both in case of 1's complement and in 2's complement, that extra carry bit indicates that the answer is positive. This is very, very important. Extra carry bit in this ones complement and twos complement indicates that the answer is positive. So therefore, absence of this extra carry bit indicates that the answer is negative. Therefore, you notice that this 1011 is not the answer. We expect that the answer will be somewhere around -5. Okay. So the moment you are seeing this, it is indicating the answer is negative. But does it mean that the answer is useless? No, it is not. So in such a case, what to do? You again take the ones complement or the twos complement, depending on what case it is. Since we are dealing with twos complement, what we will do is we will take the twos complement of the answer. So therefore, 2c of 1011 is how much? The ones complement is 0, 1, 0, 0. So the twos complement will be 0, 1, 0, 1. So this is nothing but 5 in decimal. Absence indicates, and absence of carry indicates answer is negative. And to actually get the magnitude of the answer, you have to take the twos complement again. So this means answer is -5, which is what we expect. Let us take one more example. Let us take one more example. Let us take a slightly bigger numbers. Let's say we try to do 16 in decimal minus 20 in decimal. We expect then the answer should be -4. Now let us try to do this in binary using twos complement. So therefore, let us first convert. So 16 in binary is 1, 0, 0, 0, 0. And 20 in binary would be 1, 0, 1, 0, 0. So therefore, to convert it into twos complement, we need to first take the ones complement. Oops. This will be, I'm sorry, I made a mistake. 1 plus 1 is 0 with a carry of 1. 1 plus 1 is again 0 with a carry of 1. This will be 1. This will continue to be the same. Okay, so this is the way. This is the twos complement of 20. So therefore, we need to add it to 16. So therefore, 1, 0, 0, 0, 0 plus 0, 1, 1, 0, 0. So what you get over here is 0, 0, 1, 1, 1. Once again, 5-bit number over here, 5-bit number over here. The answer is still 5 bits. That extra carry bit is not there. So this indicates answer is negative. So immediately I'll put a minus over here in the answer. So therefore, as per rule, we need to take the twos complement of this. So the twos complement of this will be how much? Ones complement will be 0, 0, 0, 1, 1. Twos complement will be that plus 1. So the answer is 0, 0, 1, 0, 0. So this indicates it is 4. Therefore, the answer is -4. This is how you can do twos complement subtraction to handle negative numbers also. Right? So this brings us to another question. In general, how does a computer handle negative numbers? How does a computer handle negative numbers? Well, in case of positive numbers, we can just write the number in binary as it is. But then there should be some kind of an indication or some circuit or some kind of a value which indicates that the result is negative or the number that we are trying to store in the computer is negative. So therefore, let us look at the next particular part of the discussion. Or not indicating, I'll say handling negative numbers by a computer. So the first technique is called as an n-bit signed magnitude representation. N-bit signed magnitude representation. So in that case, what this means is if it is an n-bit number, in binary there will be n number of bits. So therefore, if it is a binary number, there will be totally n number of bits. So what is done is that the numbering is done with respect to powers of 2, 0, 1. So if it has n bits, this will be n minus 2 and this will be n minus 1. Okay. So this indicates a total of n bits. Now, in the case of the signed magnitude representation, the MSB, that is the n minus 1th bit, is called the sign bit. This is the MSB, or the most significant bit. So they say that this will indicate the sign bit and the remaining n minus 1 bits will indicate the magnitude. These indicate magnitude of the number. So therefore, the sign bit is used this way. If it is 0, it indicates positive. If it is 1, it indicates negative. Right? Now, when we have an n-bit unsigned magnitude, unsigned, that means there is no sign bit. That means you can represent numbers which are only positive. In that case, the n minus 1th bit also contributes to the magnitude of the number. Let's look at this with an example. For example, 4-bit unsigned magnitude. Four-bit unsigned magnitude representation. In that case, my smallest number will be 0000 and my largest number will be 1111. This is nothing but 0, this is nothing but 15. This is smallest and this is largest. Alright. But now if we say it will be now a 4-bit signed magnitude. So 4-bit signed magnitude means what? Four-bit signed magnitude means the MSB will be for the sign. MSB will be for the sign. So therefore, let me call it 0, 1, 2, 3 in terms of powers of 2. So this will be the sign bit. So the largest possible number will be a positive number whose sign is 0 because it's positive, and the magnitude will be 111. This indicates plus 7, which is the largest. The smallest will be a negative number, which means that the sign magnitude, the sign bit will be 1. and the magnitude will still be 7. This indicates minus 7, which is the smallest number. So therefore, let us try to write all the numbers from minus 7 to plus 7 using this. So let's start from here. Plus 7, plus 6, plus 5, plus 4, plus 3, plus 2, plus 1, 0, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, and minus 7. So here, plus 7 as we know is 0, 111. Plus 6 is 0, 1, 1, 0. Plus 5 is 0, 1, 0, 1. Plus 4 is 0, 1, 0, 0. Plus 3 is 0, 0, 1, 1. 2 is 0, 0, 1, 0. 1 is 0, 0, 0, 1. Now comes the fun. What about 0? Is 0 a positive number or a negative number? In this case, 0 I can write as plus 0. Minus 0 I can write as 1,000,000. So therefore, there is some ambiguity in case of 0. Minus 1 is pretty straightforward. Minus 1 is 1, 0, 0, 1. Minus 2 is 1, 0, 1, 0. Same as my plus 1, but the sign bit has changed. Similarly, minus 2 is same as plus 2, but the sign bit has changed. So minus 3 will be same as plus 3 with a 1 as the sign bit. So it's 1, 0, 1, 1. Minus 4 will be 1, 1, 0, 0. Minus 5 is 1, 1, 0, 1. Minus 6 is 1, 1, 1, 0. Minus 7 is 1, 1, 1, 1, which we had already established. That is why this is quite simple to understand. But the problem is case of 0, where there is ambiguity. 0 can be represented in two different ways, a plus 0 and a minus 0. And therefore, this ambiguity sometimes can cause problems. So therefore, the signed magnitude representation is not much used these days. Some of the early calculators in the 1970s and 80s did make use of signed magnitude representation, but they had their own set of problems. So therefore, the next question which we should ask ourselves is that one technique which we looked at, that is the n-bit signed magnitude representation. Is there any other way in which we can represent both positive and negative numbers? Yes, there is. And that is called as n-bit 1's complement sign bit representation. Now let us take an example where n is 4, same as last time which we took. In that case, let's call it as number 2. This is the second technique we are looking at. Let us write all the positive numbers: plus 1, plus 2, plus 3, plus 4, plus 5, plus 6, plus 7. Here it is exactly the same as that of the simple sign bit representation. So plus 1 is nothing but 0, 0, 0, 1. Plus 2 is 0, 0, 1, 0. Plus 3 is 0, 0, 1, 1. Plus 4 is 0, 1, 0, 0. Plus 5 is 0, 1, 0, 1. Plus 6 is 0, 1, 1, 0. Plus 7 is 0, 1, 1. So far it is quite the same as that of a simple 4-bit sign bit representation. That is why we are not going above 7. We have to represent the negative numbers also. So therefore, let us try to do minus 1, minus 2, minus 3, minus 4, minus 5, -6 and -7. All that you need to do is simply take the ones complement of this entire 4-bit number. So the ones complement of this will be 1110. Ones complement of this will be 1101. This is 1100. This is 1011. This is 1010. This is 1001. And this is 1000. The next question is, what about 0? So once again, plus 0 I can represent as 0000. But minus 0 will be 1111. Once again, there is ambiguity. Once again, there is ambiguity. Although we don't have to worry about the sign bit now, because the sign bit is directly encoded into the number itself, where if you take the complement of the positive number, you automatically get the sign bit. That is one advantage. But again, this ambiguity is there. Once again, let us take a look at the next best possible thing. The third technique is what is called as an n-bit 2's complement sign bit representation. Let's take again n equals 4. So again, let's write down all the positive numbers: +1, +2, +3, +4, +5, +6 and +7. All you need to do is write their 4-bit form, which is same as 1's complement. So far it is the same. Now let us write -1. All you need to do is take the 2's complement of this. So -1 is the 2's complement of +1. So 1's complement is 1110. So this will be 1111. -2 will be 1101. -3 will be 1110. Let's just check once. So -4 will be the 1's complement of this, that is 1011 plus 1, that is 1100. Likewise, -5 will be 1011. -6 will be 1010. And -7 will be 1001. Now let us see the point of contention. So let's look at +0. +0 is what? 0000. -0 is what? The 1's complement plus 1. That is, so in 2's complement we normally ignore this. So what you notice is that +0 and -0, now they have the same meaning. Now they have the same meaning. Moreover, whether or not you ignore this one over here, what is happening is that there is this extra additional bit which has come, which is violating the n equal to 4 requirement. So with the 2's complement sign bit representation, there is absolutely no ambiguity about 0. +0 and -0 are one and the same. They are 0000. That is distinct. Okay. Moreover, this has another advantage. What you notice is that over here, the MSB is still the sign bit, and here also the MSB in each case is a sign bit. The powerful thing about this 2's complement sign bit representation is that it is not only being able to denote the sign bit, but we can use it for mathematical operations also, along with the number. Let us take a look at it. Let us say I have plus 7 plus minus 4. This is the operation I want to do. So in 2's complement, plus 7 is written as 0, 111. And minus 4 is written as 1100. So therefore, if we want to do this, we can simply do the addition. The answer is 3, which is what we expect. So therefore, we have encoded the sign bits also and use them as part of our mathematical operation. This is a very, very powerful feature of the 2's complement. So I encourage you to try out some more examples by yourself and understand more clearly how it is working. So in this particular lecture, we started the discussion on binary subtraction and we saw what is the 1's complement and 2's complement technique to avoid the borrows. You can do the same thing in decimal, except that they are called 9's complement and 10's complement. Thereafter, we looked at various ways to represent positive as well as negative numbers using something called as a signed magnitude representation. Thereafter, we saw signed magnitude representation using 1's complement as well as 2's complement.